Welcome everyone, my name is Natalia. I created a quick tutorial to show you how you can transform a Python implementation into high-performance pricer, achieving 300x speedups with just a few code lines, and that can be done using AI. We'll use average Asian option under Geometric Brownian Motion in our example. That's a classic Monte Carlo pricing problem that's compute-intensive and common in production systems. Well, Python is excellent for prototyping. It's readable, it has great libraries, and it lets quants iterate quickly. But performance? That's the Python's weakness. A naive pricer can take 4 minutes to price just 10 trades with Greeks. Python plus AADC solved this. You keep Python's ease of use for prototyping, but gain performance exceeding hand-optimized C++. Some teams even use this approach for greenfield production libraries. They write them in Python and deploy with AADC. So, AADC stands for Automatic Adjoint Differentiation Compiler. It's MatLogica's technology that uses JIT compilation for Python or C++ to produce optimized code. It computes exact derivatives via a joint method, and it parallelizes using multithreading and vectorization. Well, you might ask, why don't I use AI to optimize my code? But here's a problem. AI can introduce subtle bugs. I've seen AI optimize accumulation order, breaking numerical results across platforms. Or it might use NumPy broadcasting that looks clever, but allocates gigabytes of temporary arrays. AADC is mathematically proven. It uses the same operations and achieves the same results, but faster. And to be clear, I'm not suggesting AI should write your models or replace quants. If you already have a working model, skip ahead to part 2 on AADC integration. What follows is just a convenient way to generate a baseline implementation for this demo. To start, I want to have a model that I will later enable with AADC. As I don't have any model by hand, I will use AI to generate such model. Here I have a specification for an Asian option, which shows the Geometric Brownian Motion dynamics and discretization. It shows the averaging rules for the option. It explains what Greeks need to be computed, and that's delta, Vega, and rho, and performance measurement criteria. We intentionally ask Claude not to implement any optimizations so that we can compare apple to apple. And we show exactly the calculation steps that needs to be done so that whatever language we choose to generate this model for, we get the same results, and no rounding and no skipped steps and so on. Well, now we have the ground rules set in the Claude MD file, and let's ask Claude to generate a Python pricer for Asian option that we have defined in the Claude MD file, and compute all sensitivities using bump-and-reprice. So, Claude will now generate a Python implementation with explicit loops over trades, scenarios, and timestamps. It takes Claude about 4 minutes to do that. And here we go, we've got the results, and now we can run the actual model with some parameters. Let's run it for 10 trades for 50,000 scenarios. Fast forward, so it took us 255 seconds to price the Asian option with Greeks, and that was just 10 trades and 50,000 scenarios. In real life, you probably want to run 500,000 or 1 million scenarios, and your portfolio will be much larger. So this is not usable in production, but you have a very quick prototype. Let's move on to part 2, which is integrating AADC. A quick reminder on how AADC works. It uses operator overloading to extract the valuation graph on the fly, and then it compiles it into efficient machine code for both the original function and the adjoint function to generate sensitivities. As you can see, this compilation step is very important because it's now part of your overall execution, and it needs to be very fast. We've done some benchmark comparing us to popular machine learning tools such as TensorFlow and PyTorch, and you can see the results here. So what do we need to do to integrate AADC? Well, as a first step, we need to replace the doubles with MatLogica idouble. Then we need to record the function, which means execute the function once and instruct AADC to start and stop recording. And after that, you need to use this new regenerated kernel instead of your existing valuation function. To start with, I've created a Claude MD file again that has the instruction on how to integrate AADC. So we're saying that this agent is an expert in integrating AADC, and we provide instructions on how integration has to be done. We show how the main Monte Carlo loop has to be identified, what are the inputs, how they have to be marked. We explain that double needs to be replaced by I-double, and how evaluation needs to be done. The file also includes some recommendations and some pitfalls so that Claude can troubleshoot any integration issues itself. So let's ask Claude to generate a MatLogica AADC enabled version of the pricer that we created on a previous step. Or if you have your own pricer written in Python or C++, you can do exactly the same and just ask Claude to do the integration for you. A quick note, this approach of integration using AI should only be used for prototypes or some quick examples. We don't recommend using it for production systems, and you should rather use MatLogica's official integration scripts, debugging tools, and other toolkit features for real-life integration projects. And less than 3 minutes later, our integration is complete. Let's run it. So we paste the instruction here. Oh no, we're getting an error. Well, let's try and fix it. I'll just copy the error from the terminal and feed it to Claude. We'll see what it does. AADC is not installed, but Claude will solve that easily because it's available to install using pip install. And we've got some extra instructions that we need to run, so let's launch it. Here we go. And the results are, it took us 0.7 seconds to compute prices and risk for 10 trades over 50,000 scenarios. That is 340 times faster than the Python code that we have, and we get all the Greeks that match the Greeks computed using bump and revalue in the original Python example. Let's have a look at the code changes and what is the difference between the basic Python and our implementation. So to start with, we've got the simulate path method that is identical across the two, and this is where your main math sits. Then we have the kernel recording part, which is only relevant to AADC because obviously there is no kernel. And here we mark inputs and outputs and run the simulate path method. And then we stop recording. And similar with record kernels for Greeks, we mark the inputs, but we mark them differently because they are differentiable. And we record. Then for the price functions, the changes are minimal. In the case of AADC, we call the evaluate method. And in the case of Python, we call the simulate path method we have. When we compute sensitivities, in case of AADC, we call the evaluate function once, but in the case of Python only, we call the simulate path function 7 times. And let's have a look at the total number of lines. So in the case of MatLogica, we have 392 and 367 lines in pure Python. Few more caveats. Well, in this example, we just wanted to have apples-to-apples comparison against Python, and therefore we recorded the kernel on the trade level. If you want an optimized solution, you'd probably record it on a portfolio level. Let's say every morning you generate the kernel for portfolio, and then you can feed it with a stream of live prices and volatilities. The second thing is that here we recorded the strike and maturity date as part of the kernel as an input, but normally you would have it hard-coded as a constant because you would have interpolation based on these two factors, and this would also improve the performance. Let's look at the performance. So the naive Python implementation for 10 trades took about 6 minutes, and the AADC implementation was just 0.7 seconds, which gives you 345x speed improvement. I haven't run the Python implementation for 100 trades. It would have taken longer than half an hour, but MatLogica AADC took 6.9 seconds with one thread and 1.9 seconds with 16 threads. If you add more threads or more scenarios for AADC, it will scale linearly. As you can see, the implementation scales well with a number of threads, almost linearly. So to summarize, you just saw how we were able to convert a Python script into AADC-enabled Python, and it took us less than 20 lines of code, which is less than 1% of the code line. And we used Claude to generate this integration for us, so it took just 3 minutes to perform the integration. And as a result, we've got the speedups of over 300, and we compute all sensitivities automatically using AAD. The source code for the benchmark is available on request, and I can also provide you with the MD files that have been used to generate both the original function and the AADC integration. We have a small website that demonstrates this benchmark in a bit more details, and you're welcome to try it. You can also request your own benchmark that we will do in the same manner as we did this one, just for quick prototype purposes. If you want to try AADC, you can go to MatLogica.com and look at the code examples at top right, or you can do pip install AADC in your VS Code and move from there. If you have a large code base, perhaps millions lines of code that is 10 or 20 years old, you would typically use AADC integration scripts and the toolkit that we provide with AADC, which has debugging, branch management, and other useful tools when you're dealing with real-life projects. But if you want to do a quick start and just try it out, then you can use AI and the approach that I demonstrated here. Thank you and goodbye.